Phasor representation of alternating quantities. Phasor representation, first, what is phase? For example, this is the alternating quantity. And what is phase? Phase is the fractional part of time period or angle through which the alternating quantity is advanced from its selected zero position. For example, let us see here. The alternating quantity of this current is in phase of pi by 2 or t by 4 time. If it is here, it is in phase of pi or t by 2 time period. Next is phasor. Phasor is a line of definite length whose length is equal to the maximum value of the alternating quantity. That phasor is representation of your this phase by a line of definite length, and length is equal to the maximum value of the alternating quantity. For example, it is for current. Now, if this phasor will rotate with a constant angular velocity, we will get this. At 0, value is 0, maximum, value is maximum, negative direction, it will be maximum at 270 and again 0. So, phase is a line of definite length rotating in anti-clockwise direction with an angular velocity of omega will give the representation of this wave shape. For example, we want to represent phasor for voltage, so this is VA. For current, this is I. Angle will represent the phase. How much your alternating quantity is in phase with reference to its initial position or with reference to its reference point. Next is phase difference. Phase difference is the difference in phase of two alternating quantities. For example, we have the voltage or current, and let this V be represented by Vm sine of omega t, I be represented by Im sine of omega t minus phi. Now we can draw the wave shape for them also. Let this be the voltage V. Now, this is lagging by a phase angle of phi. So, this is current. Im sine of omega t minus phi Vm sine of omega t. So this phi is the difference in phase. So this phi is the difference in phase of two alternating quantity. That is difference in their selected zero positions, their positive difference in their maximum position values. It will be also same. It will be phi. Again, their zero positions or negative value position. So this is the phase difference. Difference in phase of two alternating quantity is known as phasor difference. Important one, phasor diagram. We have discussed that your phasor is represented by a line whose length is equal to the maximum value of the alternating quantity. For example, this is the phase difference. How will represent with the help of phasor diagram? We have discussed that phasor is a line. Let this be the line Vm. What is the difference in phase? Phi. And your current is lagging by a phase angle of phi. This is the maximum value of the current, phi. Or we can represent it, let this be Im. If this current is Im, means your current is lagging by phase angle of phi, means your voltage is leading by a phase angle of phi. So we can represent it like this. So this is the phasor diagram. But generally, as we use it, or we measure the electrical quantity in terms of their RMS values, or the quantities are specified in terms of RMS values, so we will draw the phasor diagram in terms of their RMS value in place of their maximum value. Because the phase angle between their RMS value would remain same as the phase angle between their maximum value. So actually or practically we draw the phasor diagrams in terms of their RMS value. So this one is the important one, because in next unit also in machines or transformers we will use this phasor diagram. 3-phase circuits we will use the phasor diagram. So this one is the important, and this is nothing to just representation of your phasor showing a certain phasor difference. Voltage represented by V, phi represented by V. So it doesn't require that we mention this is the RMS, IRMS. If we simply mentions this is V or this is I, well understood that this is the RMS value of the voltage, I the RMS value of the voltage. If it is the maximum value, then we have to specify it that this is the maximum value or this is the average value. The final, the phasor diagram would be terms in terms of their RMS value. Now, for example, we want to add two alternating quantities. Now, you just want to add the alternating quantities. Addition of alternating quantities. We have two alternating quantities. Let E1 be EM1 sine of omega t and another EM2 sine of omega t minus phi. For example, you have to add these alternating quantities. What would be the resultant? Resultant would be E m sine of omega t plus minus some angle alpha. This result we have to find. So that can be added up with the help of our phasor diagram. Just draw the phasor representation. This is the E1. Okay. Let represented by their maximum values EM. This one is the EM2 is lagging by phase angle of phi. Let this be EM2 and this angle is phi. What would be the resultant? EMR. And that can be find out, just draw the parallelogram and find out this resultant. We have drawn the parallelogram. So this one is the EM2. Extend it and draw a perpendicular. What is this angle? This angle is phi. So this angle would also phi. So this can be resolved into two components. One is horizontal and that would be EM2 cos of phi, and this is EM2 sin phi. Now, what is EMR? Yes. EMR is base का square plus perpendicular का square. तो base is EM1 plus EM2 cos of phi plus EM2 sin of phi under the root. This way we can find out the resultant EMR. And tangent of alpha, is perpendicular by base, and perpendicular is EM2 sin of phi divided by base is EM1 plus EM2 cos of phi, or alpha would be tangent inverse if you want to subtract them. Same method would be applicable. Just we have to do, we have to reverse the phasor to be subtracted. Here we have resultant was E1 plus E2. If we requires subtraction E1 minus E2, what we will do? We will reverse the phasor. And then we will draw the parallelogram to find out the resultant. We will get the subtraction result. But the efficiency of this parallelogram method is we can add two alternating quantities at a time. To add more than two alternating quantities or subtract more than two alternating quantities, we require some another method, that is method of component, that is named as method of component. In which number of alternating quantities, let this one be the one alternating quantity. Let us take this x o x dash y o y dash. I1 with reference, let the angle be phi 1, I2, phi 2, I3, phi 3, and so on. So what would be the resultant? IR. Your IR is sum of horizontal component, sum of vertical component, sum. Square under the root. And your phase angle would be, for example, this is the resultant. And this angle be phi. Or we have, in last case, we have considered this alpha. Let it be alpha. So what is the tangent alpha? Sum of y components divided by sum of horizontal components. X means horizontal component, y be vertical component. Now, x component. For example, in this example, what is the x component? Sum of horizontal. This I1 can be resolved into two components. What will be the value of horizontal component? I1 cos of phi. This 2 I2 cos of phi 2 plus I3 cos of phi 3. Sum of vertical components. Yes. For example, this we have considered this y as a vertical component. Yes. I1 sine of phi 1. This resolved into horizontal component. At horizontal value of this I1 was I1 cos of phi 1, and value at this component is I1 sine of phi 1 plus I2 sine of phi 2 plus, yes, now I3 sine of phi 3 would be here, but we are considering the values at this OY axis. So we will reverse it, the sign would also reverse. So that's why in place of minus plus we have considered this I3 sine of phi 3, because the value of here is I3 sine of phi 3, and when this value is considered here, it will becomes minus I3 sine phi 3. Now IRB, just I1 cos of phi 1 plus I2 cos of phi 2, I3 cos of phi 3 plus I1 sine of phi 1 plus I2 sine of phi 2 minus I3 sine of phi 3 under the root. Tangent of phi or tangent of, we have alpha. Yes. I1 sine of phi 1 plus I2 sine of phi 2 minus I3 sine of phi 3. I1 cos of phi 1 plus I2 cos of phi 2, I3 cos of phi 3. And alpha is tangent of inverse. Now we can simply find out the resultant. That can be the RMS value, that can be the maximum value, that doesn't matter. If you have the maximum values, so you can represent the phasor in terms of their maximum values. If you have the RMS value, you can represent the phasor in terms of their RMS values. For subtraction, just what we will do, scheme would remain same. For example, we have to do I1 plus I2 plus minus I3. That means I3 would be this one. We will reverse the phasor in phasor position. And the angle would be now, what would be the angle? If this angle was phi, this angle was phi. What would be this angle? This angle would be 90 minus phi. This angle would be something different. So what would be the sum of horizontal component now? I1, I2 and I3. Yes, this angle is phi. Let me see. Yes. So what will be the value of here? I3 cos of phi 3. I3 cos of phi 3. So this would be minus I3, because when we represent it at OX axis, here its value would be I3 cos of phi 3. When we represent it, it would be minus I3 cos of phi 3. Likewise, at perpendicular axis, value would be I3 sin of phi 3. So this would be the difference. We will get the resultant I1 plus I2 minus I3. So using method of component, we can do addition or subtraction of number of alternating quantities. Now we have further more techniques by which we can add up, multiply, subtract, divide the alternating quantities. That is in terms of complex quantities. Complex. We know this iota, and in place of iota we just use j, and this j operator can be represented on your axis, horizontal and vertical axis. If this operator is rotated by j, or when the alternating quantity, for example, this is the alternating quantity E. If this alternating quantity is rotated by an angle of 90 degree, then the value of the alternating quantities would becomes JE. If further rotated by further 90 degree, it would be multiplied with j square E. Further rotated by 90 degree, again multiplied with j square into j. Further rotated by 90 degree, the value of this alternating quantity j for E, and value of this j or your iota is minus root 1. J square minus of 1, that is equal to minus 1. So what would be the value here? This E would becomes minus here. That is in phasor position. J cube is minus root 1 and that would be minus or minus of J. That's why we can represent it by minus J E, phasor position. Just sign would change. And J4, that is equal to 1. And that is equal to value would be E here. So here E minus E, JE minus E. So we will use this notation J to represent our complex quantities or to represent our alternating quantities. Phasor, or we can say it vector representation. Using phasor, we can represent the alternating quantities in terms of their maximum values and in terms of their RMS values, and that represents a diagram. This is V, I, V1, I1, or V1, V2, V3, showing some angle in between them to just give the picture, or we can represent them in terms of waves. For analytical purposes, we represent the phasor in different forms. So we have different forms, that is rectangular form, trigonometric, trigonometrical form, exponential form, polar form. So we can represent these alternating quantities in any of the form: rectangular, trigonometrical, exponential and polar. First, rectangular form. Rectangular form is symbolic notation of your alternating quantities. For example, this is the alternating quantity E. So that can be represented in terms of their horizontal and vertical component. So E1 can be represented by A plus, here this factor is perpendicular, mean multiplied with operator J. Let it be here E2. Let this be angle, some angle theta or phi 1. Yes, horizontal component A2 and this will be B2. How it will be represented? Value of the, now it is on OX axis, means the operator is multiplied with J square. J square means minus 1. It will be multiplied with minus 1. For example, it is here E3. Then what would the value? A3, B3. Operator is rotated by an angle of 180. So E3 would be minus of A3. Now this operator is rotated by angle of 270. So means J B3 and E4. It would be A4, B4 and similarly rotated by 360 minus JB4. So this is the symbolic notations by which these phasors are represented in terms of their horizontal and vertical components. Another form is trigonometric form. For example, let this be E. In rectangular form, we have represented in terms of A plus JP. That was E was A plus JP. Let this angle be theta. So this can be resolved, this E can be resolved in the form of trigonometric cosine of sine of the angle. This A can be replaced by E cos of theta, horizontal component. This B can be replaced by E sine of theta. So means this representation is being represented in terms of cosine or sine of the angle J sine of theta, E, or E cos of theta plus J sine of theta. The position of E may be anywhere in this 4 quadrants, so it may be represented by E cos of theta plus minus J sine of theta. Exponential form. Angle is known, magnitude is known. So this E by Euler's theorem, this cos theta plus J sine of theta can be represented by minus J of theta, or this cos of theta plus minus J sine theta is represented by E plus minus J of theta. And this in exponential form This trigonometrical form can be represented by this one, or this polar rectangular form can be represented by this. Fourth is polar form. This is just representation of this trigonometrical or exponential form in terms of their magnitude and angle. So this can be represented by E angle theta, where E is the magnitude and theta is the angle, or some sort of representation of exponential form E angle plus minus theta. So this is the polar representation, or we can convert your phasor from one form to another form as per our requirement, because our requirement may to add the phasors, to subtract the phasor, to multiply the phasor, to divide the phasor. For example, how we can convert these phasors? Let we have the phasor, your E is 3 plus J, is in rectangular. This is the rectangular. We want to convert it into the trigonometrical form. Yes, this is the E, value is 3, 4, and this angle we let it be theta. For conversion into trigonometrical form, that is E cos of theta plus J sin of theta. Yes. Our requirement is theta, and your theta is tangent theta is perpendicular by base 4 by theta, or theta is tangent inverse 4 by 3, and it would be comes out to be 53.1 degree. Magnitude, you have to find out what is E. 3 का स्क्वायर, 4 का स्क्वायर, under the root, and it will be 25 or 5. So in trigonometrical form, it would be 5 cos of 53.1 degree plus J sin of 53.1 degree. You want to represent in terms of exponential form. It would be 5 e raised to power minus j, angle is 53.1 degree. And in case of polar form, it would be 5 angle 53.1. Now, your addition is simple or subtraction is simple in case of your rectangular or trigonometrical form. You just add real components and imaginary components or quadrature components simultaneously. Likewise for subtraction also. For addition and multiplication and division, polar form is gives the better results or time saving. For example, you want to add multiply two alternating quantity. One is 5, another is, let it be 40 degree. So what would be the multiplication? You will multiply the magnitudes and add up the angle. It would be 53.1 plus 40 degree. That would be 93.1 degree. Division 5 angle 53.1 and 4 angle 40 degree. So what would be the division? 5 by 4 angle 53.1 minus 40 degree. So that makes the calculation easy. That is the applications of these representation of phasors or alternating quantities in terms of complex nature. Let us take some example for addition and subtraction of alternatives. Addition and first addition of alternative. We have two alternating quantities. E1 is A1 plus J B1. E2 is A2 plus J B2. In their addition is simple. So what would be the resultant E? E would be A1 plus A2 plus J B1 plus B2. If you go for subtraction, no, first addition only. If you have the rectangular trigonometrical form, so it would be E1 cos of theta 1 plus J sin of theta 1 and E2 cos of theta 1 plus J sin of theta 2. Now, where E1 and E2 here are the magnitudes. Now, E1 cos of theta 1 plus E2 cos of theta 2 plus J E1 sin of theta 1 plus E2 sin of theta 2. So that becomes somewhat complicated. But if we go to polar form, E1 is represented by E1 angle theta 1, E2 is represented by E2 angle theta 2. How you will add? E1 angle theta 1 plus E2 angle theta 2. You have to convert them in this or in this, then you can add only. Now, likewise, for subtraction, it is simple to have the subtraction of these two alternating quantities. B1 minus B2. Likewise here, What we have to do? First, go to the trigonometrical form, and that trigonometrical form gives the result in terms of rectangular form, and then you can subtract. Because if you know the value of the angle, the sine of angle you can find out easily. Next is multiplication of the alternative quantity. Now we require E1 into E2. How you will multiply that? E1 into E2. E would be A1 JB1 A2 JB2. So you will multiply them. A1 A2 plus J A1 B2 plus J B1 A2 plus J square B1 B2, or this would be A1 A2 minus B1 B2 plus J A1 B2 plus J A2 B1. It will becomes somewhat lengthy process. But if you go the multiplication likewise in trigonometrical form, you have to do the same job. But in the polar form, this E is represented by E1 angle theta 1, E2 is represented by E2 angle theta 2, and this E would be equal to E1 into E2 angle theta 1 plus theta 2. Just we will multiply their magnitude and add up the angle. So this polar forms makes your calculations simple. Division. E1 by E2. Yes. In case of rectangular form, we have to rationalize them. We will multiply and divide with their conjugate, and then we will simplify it. If we have to divide in terms of their polar form, E1 by E2, that is equal to E1 angle theta 1 divided by E2 angle theta 2, and that would be equal to E1 E2 theta 1 minus theta 2. So this is the simple. Division becomes simpler in your polar form. So these are the applications for addition, division, subtraction and multiplication.